Hello again, geometry. It is Mr. Zabo, and we are moving on to section 4.1. We are going to talk about detours, and we're going to introduce midpoints from a little more of an algebraic standpoint as well. But first, a detour. It's essentially a proof within a proof. What we're talking about is we can't prove, say, in this example, that these two triangles are congruent because we don't have enough information. If I want to show triangle BEC is congruent to triangle CED, I need three pair of congruent corresponding parts. But what I know is just this. I don't know enough, and I could say that I have reflexive property in here, or that EC is congruent to EC, but I don't know anything about BE and ED based on my given statements. I can't assume anything from the diagram, so I can't do side, side, side. I can't assume anything about my angle measures being congruent, so I don't have any of my other methods. But I can do a proof within a proof to get there. And what that's going to look like is to first prove that triangle ABC is congruent to triangle ADC. I can use all of the corresponding parts of those two congruent triangles then in any other proof. Once I do that, I will know, for example, that angle ACB is congruent to angle ACD, and then by side angle side, I have congruent triangles BEC and DEC. So that's how I will write this proof up, but there are a few other ways. That's the fastest route to do this. So if I were writing this proof up, I know that these are given, okay, and then I'm going to state that segment AC is congruent to itself by the reflexive property. And from here, my triangles are now congruent, making sure I name them appropriately. So if I name the first one triangle ABC, the second one would have to be triangle ADC, and that is side, side, side congruence. Again, I'm using this angle conclusion now because my triangles are congruent. That angle ACB is congruent to angle ACD because corresponding parts of congruent triangles are congruent. Now I have three corresponding, well, I have two. I have AB being congruent to AD, which I don't need because that's not part of triangle BEC. I have BC congruent to CD. I have these angles congruent. I stated reflexive, but I stated segment AC. I also need to then completely restate this, and not with A, but with segment EC being congruent to itself. That is the side of my triangle. So I need to use reflexive again with that new statement. Now those three corresponding parts allow me to conclude that triangle BEC is congruent to triangle DEC by side angle side congruence. Okay, so I have two different triangle congruence proofs. Triangle ABC congruent to triangle ADC because of side, side, side congruence. That allowed me to use that triangle to find angles that I could then use in my second triangle congruence. And that's what a detour proof is. Okay. So this is straight from your textbook. The procedures for doing detour proofs, we first want to determine if our triangles that we must prove are congruent. Okay. And do we have enough information? That's if we're asking to do triangles. We might be asked to do sides, like and then which triangles do I need to prove congruent to prove that those sides are congruent using CPCTC. Okay. Then I'm going to attempt to prove that they're congruent. If I can't because I have a lack of information, then I must take a detour, and that's what steps 3, 4, and 5 here represent, is our detour. Okay, so I'm going to determine which part. Determine which parts I must prove to be congruent to establish that the congruence of my triangles. So which are my three sides or parts that or angles that I'm going to use? Consider all of them. I might need sides, I might need angles, I might need a combination. Okay? And then find the triangles that are going to give me what I need. Okay? Once I know the triangles, go ahead and prove that those two are congruent. And then I can use CPCTC to finish the proof. Okay? All right, let's put that into action on the next page. Here's my diagram. I have been given that I have circle O, and I have angle B is congruent to angle C. So I'm going to, step one, what is it that I need to prove? Well, if I'm trying to prove AO bisects BC, I want to prove that segment BE is congruent to segment EC. That's going to allow me to prove this. Well, I can do that if I have triangle ABE congruent to triangle ACE, but I don't have enough information. How do I know that? Well, I know it's a circle. I know angle B is congruent to angle C, and these are isosceles triangles, so that allows me to conclude that segment AB is congruent to segment AC. I know I have the reflexive property, but that's all I know. And this is angle side side. That doesn't work. Okay, so I need more. These are the three sections or segments and angles that I know. But in order to make this proof, I need more. I don't have enough. So if I could somehow find, let's say, this angle, I'll call it angle 1 and angle 2, to be congruent. Then I'd have side angle side, I'd have angle side angle, I'd have a lot of different ways to do this. Okay? So how do I do that? So let's say if I can get angle 1 congruent to angle 2, then I can make this proof. So there is something missing that I can still do. Because I have a circle, I can draw segment BO and segment CO. 2 points means I have a line, and then they're congruent because those are my radii. So if I do that, I draw those two segments, which I know are congruent, I am going to be able to show that triangle AOB is congruent to triangle AOC. Then angle 1 will be congruent to angle 2 because those are corresponding parts of congruent triangles. And then I have enough information to complete the proof. So that's the thinking, the thought process, behind all of that. What I'm going to do is ask you to pause the video, see if you can write that up in a 2-column proof. All right, and here's what that 2-column proof should look like. So we have to go through the whole process of proving triangle AOB congruent to triangle AOC, which means I need to have my radii congruent. I have to state that I drew the radii. Okay. Then the fact that my angles were congruent allowed me to conclude my sides were congruent, and then I have my reflexive property. That got my two bigger triangles congruent. I'm using that to prove angle 1 congruent to angle 2. And then I already had angle B congruent to angle C and segment AB congruent to segment AC, so I can use those again. I don't need to restate them. And 4, 5, and 8 are my three corresponding sides of and angles of triangle AEB and triangle AEC to use angle side angle congruence. Then the two sides that I need are congruent, and I have two congruent segments implies bisect. All right, Last thing I want to talk about real quick is midpoint. We've defined midpoint geometrically as a point that divides a segment into two congruent segments. We want to make sure that we review and define this algebraically again as well. I believe you've done this in algebra, but let's take a couple of minutes to review it. Okay, if A and B are my points, my ordered pairs, and the midpoint then is the average. It's the average of my x coordinates, average of my y coordinates. That's what we've done in algebra. We might make this a little bit more complex here in geometry, like an example like this. If I want 1/16th of the way from A to B, and I know what A and B are, I'm going to actually have to use my midpoint formula multiple times.